Thank you so much, Anna, for the very kind introduction, and thank you and Johannes and all the other organizers for the invitation. This is great. So yeah, today I'll be talking about quantizing neural networks, and in particular about a greedy, computationally efficient algorithm for doing that. So most of this work is joint work with my now graduated PhD student, Eric Leibrand. And some of the work that I won't give in too much detail, but I might allude to, is with my current PhD student, Jinji Zhang. So let's see. So we all know that neural networks and deep learning have been extremely successful in recent years in a very large range of tasks, games, fraud detection, natural language processing. They've been used in technologies that are still futuristic, self-driving cars and things of that nature. And the list goes on and on and on. And while these things have been extremely successful, this success hasn't been entirely free. So it comes at a cost, and sometimes this cost can be large. So just as an example, this is just a picture showing on the x-axis time, and on the y-axis, basically the accuracy of various algorithms at classifying images in the ImageNet. And we see, for example, in 2020, that the most efficient one, or the most accurate one, had something like 480 million parameters. The second most accurate one had also something like 480 million parameters. Some others had fewer parameters that were still pretty good. And then even if you went down the list, you would see that the number of parameters tended to be pretty high. So they were achieving good results, or they are achieving good results, in fact, great results, but they're throwing a lot at the problem. They're throwing a lot of parameters at the problem. Okay, so lots of complexity, and this is not really restricted only to ImageNet and image classification, but like it extends to a whole bunch of applications, natural language processing and others. So this is one particularly egregious example. This is an NVIDIA network, which has something like 8 billion parameters and takes something like 33 gigabytes to store on disk, takes forever to train, consumes a lot of power, et cetera, et cetera. So there's this trade-off between the success on the one hand and the cost on the other. So we're motivated by questions related to reducing the cost associated with this complexity. So what do I mean by this? What I mean is, if you're going to implement this neural network, it's ultimately just a function. And it's a function with 480 million parameters in this example that we gave. And so each one of those parameters does something. It either multiplies something or adds something, or it's part of some nonlinear component of the network. So in other words, each one of those parameters is associated with the computational complexity of the operation it's associated with. So if it's a 32-bit parameter and you're multiplying by it, that means you're multiplying by a 32-bit integer. That means that you're spending power. That means that if you have a battery, that you're consuming the battery. If you have a device, it's costing you something in terms of power, in terms of just building the device. So the question is, can we go and replace these, for example, 32-bit parameters, these 480 million of them, by much simpler choices like negative ones, preferably zeros and ones, which have much lower costs associated with them. So multiplying by 0 is essentially no cost. Multiplying by 1 or negative 1 is very low cost, and so on and so forth. So we want to ask the question, if you hand me a neural network, is there a quantized neural network where the parameters take on values in these small sets that approximates it well? If so, can I construct this network that exists? Can I find it in a reasonable amount of time? So the reason this question is important is because I have 480 million parameters. And to know that it works well, I have to know that it works well on data. And that means that it has to work well on large data sets, because that's the context that we're interested So if I'm feeding it large amounts of training data, and I have 480 million parameters, and I come up with something like an SDP to do my quantization or something like this, then a polynomial cost hitting parameters that are in the hundreds of millions might be just completely out of the realm of applicability for doing this. So then the question is, can I do it in a reasonable amount of time? Meaning something like linear in the number of parameters and in the number of data points. So I have to pass through all my data, I have to pass through all my parameters, but I don't want to do too much more than that. And then, of course, does my algorithm work? Does it generalize to new data? So those are the questions that we would like to at least somewhat start to address, and we would like to start to address them from a theoretical point of view. And the reason is there are algorithms out there that are empirical and they work well, but we don't necessarily have a good theoretical understanding of them. So we'd like to bridge this gap also. Okay, so here's our setup. This is some complicated neural network that we're trying to approximate. We're going to define an L layer neural network to be a function. Each layer is a composition of something nonlinear and something affine. And I stack capital L of those things. And for simplicity here, each phi is a component-wise nonlinearity, something like a ReLU function or something like that, acts element-wise. And each one of those affine sublayers is basically something that takes an input, multiplies it by a matrix, and adds a bias. So the matrices are indexed by the layer L, and so are these vectors of biases. And the one thing that you will probably notice is that I've chosen here to go with like a transpose notation compared to what we're normally used to. We're normally used to doing matrix times vector rather than transpose vector times matrix. And the reason I'm doing it this particular way is because the object that I care about is the weight. That's the thing that I want to replace with something quantized. So it's going to be just a little bit more convenient to write it down this way. Okay, so a little bit more on the setup. Just in order to not have to carry around this cumbersome bias term, we're going to make the very simple observation that X transpose W plus B transpose can be written as in a one lifted higher dimension as X transpose concatenated with a 1 times W with a bottom row composed of B transpose. That basically means that I can relabel this and call it my new X. I can relabel this and call it my new W, and then I don't have to worry about the biases from now on. So my goal is to replace all of these weights with quantized matrices Q. And as I said, there's been like a bunch of work on this dating back 5 to 10 years. And a lot of it is pretty successful empirically, though some of it, most of it doesn't have any real theory behind it. Okay, and some of it is really after a slightly different setting. So some algorithms are after compression, and that might be a little bit different from what we're after, where we actually want the network to be replaced by something equivalent, where it's not that I'm trying to store it efficiently and then I unpack it and then it's still expensive to implement. So I would like to quantize rather than just compress. But there's plenty of work, and as I said, the goal is rigor, theory, and empirical success. Okay, so our approach is going to be data-driven. What does that mean? It means that I'm going to start with some matrix. We're going to call it training data, but it's not training data in the sense of I use this data to train and find my weights W, but rather it's my training data for replacing these W's by Q's. And what it consists of is rows, X1 through Xm. So I have M data points, each of which is in N dimensions and not dimensions, because that's my first layer. And what I'm given is an already trained network. So one of these wonderfully successful 480 million parameter neural networks that's that already works great. And I want to basically replace these W's by things that are much easier to compute with and store so that it doesn't consume as much power and doesn't require as much memory to work with. Okay. Now, obviously, my goal is that this new network is as close as possible to my old network. So the way we're going to measure that is through the Frobenius norm. Again, this is a data-driven approach. So what we're going to say is you feed the data matrix to your unquantized neural network. It gives you some output, and then feed the same data to your quantized neural network. And what you would like is that the outputs are as close to each other as possible. So we're going to measure this in the Frobenius norm. Of course, in reality, ideally, you would like to measure this in terms of classification accuracy or whatever task you have at hand. But we're going to settle for this for now in order to be able to analyze this. Okay. So that's the goal, minimizing or getting this error as close as possible to zero. So we'll focus in on just a one-layer neural network for the moment, and we'll make the following observation. So the Frobenius norm squared that is associated with this expression can actually be rewritten as, well, in our case, just by a transpose. This operator W1 acting on X is just the matrix X acting on this difference. And by writing Q as a bunch of columns and writing W as a bunch of columns and then subtracting them, we get an expression that looks like this. And unfolding this Frobenius norm and writing it as a sum of squares, we end up with basically a sum over n1 columns of the data matrix X acting on the vector Wj minus the vector Qj squared, and then summed over all these columns J from 1 through n1. So in other words, if I want to minimize this Frobenius norm, I can settle for minimizing each one of these little L2 norms. And that basically means that I don't have to worry about, when I work with each particular layer, I don't have to worry about the entire layer in one go. I just need to worry about a particular neuron, because each one of these weights corresponds to a neuron, weight vectors corresponds to a neuron. So I can deal with it one neuron at a time. Okay, so one layer at a time, then one neuron at a time. So we started with the first layer. We decided that we can drop now these superscripts associated with the columns because we're dealing with each neuron separately. And ideally, it's pretty simple what you want to do. I mean, the goal is fairly straightforward. You basically want to find the Q that minimizes this expression. So find me, for example, if my alphabet is -101, find me the vector whose entries are -101 that minimizes this L2 norm. Well, how many of these vectors do I have? I have 3 to the n of them because each entry has 3 possibilities. And this is a horrible integer programming problem. And in general, it's going to be, you're going to have to run through all the possibilities to find the best vector. So we can't go the brute force approach. Not only that, but even if you could go the brute force approach, do you even have a guarantee that xw minus xq is going to be small? Like, is this problem even a problem worth thinking about? So let's start with this problem first. Let's figure out if it is worth thinking about, and then if it is, we'll take it from there. Okay, so discrepancy theory is a tool that comes to the rescue here. There are plenty of results there that help us out. We'll start with a very basic one, or rather not basic, but with the simplest one. And it basically says the following. Suppose you start with an alphabet of -1, and suppose that you're trying to approximate the 0 vector, meaning you're trying to come up with a Q so that xq is as close to xw as possible. Well, xw is 0, so you want xq to be close to 0. So that means you want the 2 norm of xq to be really small. So there's a theorem by Spencer from 1985 which tells you the following. It tells you that if you had a collection of columns, x1 through xn, that all lived in Rm, and all of them were like in the unit ball, then you could find a choice Q, or there exists a choice Q of vectors in of elements in -1, 1, so that the infinity norm of xq is bounded by log m. Okay, we would like it to be 0. Spencer's theorem tells us that we can get it to be log m. Now, the good news is that this log m doesn't depend on how many vectors I have, so it doesn't depend on n. Now the question is, okay, well, this theorem requires w to be 0, and it requires the alphabet to be -1, 1. What about more general cases? So there are more results from discrepancy theory that help us. There's the Komlosh conjecture, and the Komlosh conjecture tells us that if I were to replace the 0 vector by a vector whose infinity norm is bounded by 1, so this is closer to what we would like to do. You have a weight vector that's in some ball, you want to replace it with q's, and you want it to be close. Well, this tells you that you could do it, and you could end up with an L2 norm that's bounded by the L2 norm of the error that's bounded by square root of n. So again, the good news here is that it doesn't depend on n, and that's what this tells us. Okay, so since then there's been a bunch of work that plays with this result, improves it, gives you some computational ways of achieving this existence, this assumed existence. And the relevant ones, or some relevant ones, are by Banashchik, which essentially tells you that you can, here the assumption is that w is 0, you could get to something like square root log m. And more recent computational approaches by the team of Dedushkarg, Lovett, and Nikolov, and then Bansal, Dedushkarg, and Lovett, tell you that there are algorithms that allow you to find such vectors q. The unfortunate thing is that these algorithms are pretty expensive. So something like n to the 6 flops is what it costs you to run an algorithm like this. It's a semi-definite program, so if you have hundreds of millions of parameters, this is just out of the game. Okay, so they improved this, as I said, but you still need some polynomial, and here it's like it's an n cubed in terms of the number of parameters. So it's still pretty expensive, and it's m squared in terms of the number of data points. So again, expensive. Okay, so we have an answer to the theoretical question: is it possible to find networks with decent error bounds? But then can we do it in a reasonable amount of time, meaning sub-polynomial, hopefully linear? Okay. What we're going to do to hopefully do something computationally tractable is be extremely naive and extremely greedy. What we're going to do is just notice that the error vector xw minus xq is just a sum of weighted components of columns of x and weighted components of columns of x. So what is it weighted by? In the unquantized neural network, the original weights, and in the quantized neural network, it's the quantized weights. And so what we'll do is we'll try at every time step. So we're going to treat each column as a time step. And at each one of these time steps, we're going to try to make the sum as close as possible to the unquantized network. So instead of going in one go from 1 to n naught, we're going to go from 1 to 1, then 1 to 2, to 3, to 4, all the way up to n naught. And we're going to say, pick the q at each step that gets you closest to the sum that you want to achieve. So that means that at each step, you're making a choice between -1, 0, and 1. And you don't have to make a choice in this 3 to the n space that's extremely large. So this is a very simple and greedy idea. And the question is, does it give us anything useful? So in order to analyze it, or to get a better handle on it, I'm going to just write this algorithm a little bit differently. So what I'm going to say is the following. Well, just to make the assumptions clear, somebody hands you data, weights that are bounded by 1 to stay in this discrepancy theory context, an alphabet, for example, -1, 0, 1, but it could be anything. And then at each time t, what you're going to do is you're going to run an algorithm. So you'll start with an error that you initialize to 0. So this is a vector. you initialize it to 0. And then at each step, as I said, you say, my new error is the sum of the old error plus the error I commit at the current step. And I want this to be as small as possible. So pick the element of the alphabet that minimizes the error at this point, and then update the error. So what's the error? It's the old error plus the new. Great. So that's just the little system that we're going to run to quantize our weight vector. And we're going to try to get some intuition as to how it might perform. What are the things that it likes? What are the types of data that it likes? What are the types of data that it doesn't like? And with that intuition, we'll hopefully be able to do an analysis and figure out how well it does. Okay, so before I jump into that, I'll just make one quick observation, and that quick observation is that we can replace this step here, which looks like an abstract argmin step, by something a little bit more concrete. And that more concrete object is the following. I'm going to round, so this squiggly Q here is like a rounding operator. It basically says, find me the closest thing in the alphabet to its argument. And it turns out that the expression from the previous slide is minimized by essentially just rounding the scalar quantity. So what is the scalar quantity? It's the weight that I'm trying to quantize plus the inner product between the current vector, and the previous error normalized by the size of the vector. So this is not a hard equivalence to figure out. It just boils down to completing the square here and getting rid of irrelevant terms and then seeing what it ends up with. Okay, so that's the algorithm. And then we want to make sure, first of all, that this isn't an expensive algorithm. So let's check its computational complexity. Well, inner products between vectors in Rm cost something like O of m flops. I add a scalar, so that's nothing. And then I quantize a scalar, so that's nothing. These are O of 1 operations. So this thing just costs me O of m flops, and the cost is entirely in the inner products and the vector norm. And then I update the error, and that's just addition of m-dimensional vectors. So that's an O of m operation. Well, that's each particular step, and I run this for time for all the columns. So I have n columns, and that means that my computational complexity is nm. And that's great because that's the size of my data matrix. So if I want to touch all my data points, it's going to cost me nn. All right, so that is our algorithm. Now let's see how it functions on some artificial sort of contrived examples, and then we'll try to generalize from there. So let's start with like what we're calling an orthonormal walk. So the orthonormal walk is a setting where, as it sounds, all the vectors are orthonormal. So that has a particular implication. The implication is that the next vector is going to be orthogonal to the error. And the reason is that the error at every step is in the span of all the previous vectors. You can see this from the last line. So if the error is in the span of all the previous vectors and all the vectors are orthogonal, then the next vector is orthogonal to the previous error. That basically means that this inner product is 0. And that basically means that at every step, you're quantizing the weight. You're just rounding the weight. So if you have vectors that are all orthogonal to each other, you're just rounding the weight. And that's bad news because that essentially means that the error accumulates. At every step you commit an error, everything's orthogonal, apply Pythagoras, the errors just add up in the square sense. And because it's a constant and you have an n-dimensional vector w that you're trying to quantize, you end up with an error that scales like n. We don't like that. So it's scaling with the number of parameters that you have. Okay, now this contrived example can be made a little bit less contrived if you think about an adversary who's feeding you, who's shuffling the data and basically feeding you vectors x that are orthogonal to the error that you committed in the previous step. Of course, this is still contrived, but it basically means that you don't necessarily only have to be in Rm and have m orthogonal vectors for this horrible example to generalize. You don't actually need full orthogonality, you just need orthogonality to the previous error to get this to be 0 and then to get the errors to accumulate. So that's bad news. On the other hand, data shouldn't behave that way in general. It shouldn't be picked adversarially to a particular algorithm. And in fact, this plot is just to show that if I go ahead and pick my x's orthogonal to the previous error, then I do actually get this horrible scaling. It increases with the number of columns that I have. But if I then take that exact same horrible data set and I shuffle the columns, then the algorithm no longer has a problem. Because they are no longer orthogonal to the previous error vectors, and the errors no longer accumulate, and some cancellations happen that save us. Okay, so that's something. Let's look at what happens in the other extreme case, where instead of having like instead of having orthogonality, we have the opposite of orthogonality. We have collinearity. So we have vectors x that are all the same, essentially. Then in that case, without going into details, the algorithm collapses into something well known in the quantization literature. It becomes sigma delta quantization. And sigma delta quantization has a nice property that when it is stable, and in this particular case it would be, the infinity norm of so this is a typo, this should have been infinity norm. The infinity norm of the error vector would be a constant. And since this error vector is in Rm, then the 2 norm would be square root of m. And that reminds us of the bound and the Komlosj conjecture and those things. So that would be good. So the one-dimensional walk is an example of good things. The orthogonal walk is an example of bad things. So now I'll give a theorem, and then I'll skip the proof until the end. If there's time, I'll come back to it. So the theorem is this: if I'm given an alphabet, and here for concreteness, I'm just listing -101 as the alphabet, but this can be replaced by something arbitrary. -11 or much larger alphabets would be even better. And I suppose that my data has independent Gaussian columns. This can also be relaxed to sub-Gaussian and other distributions. Suppose that my weights are in the L infinity ball. Then, with high probability on the draw of the data, if I choose Q using the algorithm that I just described, you can bound the error by square root of m log n. So it's not entirely independent of the number of parameters as we would like it to be, but instead it depends on them logarithmically. But we have the nice square root that we saw before. So that's the theorem. It gives us a guarantee that the algorithm does work well when the data is random, hence non-adversarial. And as I said, the randomness assumption can be slightly weakened to nicer distribution, to other distributions. So I'll skip the proof sketch for the moment, and I will point out, as I briefly mentioned, that this is in spirit almost Komlosj. So Spencer's theorem tells you that your infinity norm is bounded by something like constant. Infinity norm bounded by constant would allow you to deduce that the 2 norm is bounded by root m, and we are getting this root m log n. So that is that. To understand this behavior a little bit better, it might be a good idea to look not just at the absolute error, but to look at the relative error, because that gives us an idea about how big this thing is compared to the actual output of the neural network. I mean, you would like xw minus xq to be small compared to xw. And because we're making an assumption about Gaussianity here, then xw is easy to get a handle on. The normalization of x shows up in the numerator and the denominator, so it doesn't really matter what the variance is, it's going to cancel out. And if you work through this quick calculation, you'll see that you'll end up with a relative error that looks like root m log n divided by the 2 norm of w. Now, if w is a well-behaved weight vector, meaning all its entries are non-zero and nice, then you expect this 2 norm to be something like square root n. So you expect that for generic vectors, the relative error looks something like square root m log n over n, which means in practical terms that if your network is over-parameterized, it has more parameters than it has than you have data points, that the error decays, the 2 norm decays like 1 over square root the parameters. So more over-parameterization gets you less error. Okay, so that's the statement of the theorem. It has some corollaries that are not too hard. Oftentimes the data, you may have m data points, but the data points may not be as complex as that. They may live in a d-dimensional subspace, but you have way more of them. Then you replace the m by a d. Ideally, we would like to replace this by some nicer notion of the complexity of the data set. But at the moment, we can't do better than this simple subspace model or unions of subspaces. But we would like to be able to control this with Gaussian widths of sets and things of that nature. I alluded to the fact that we would like to say something about generalization bounds, and here we say something simple about generalization bounds. So suppose that your data has the following singular value decomposition, and say that you get a data point that lives in the row span of your data. So each row is a data point. Your z is something that lives in the row span of your data, and you want to see what the error looks like. You can show that the error still is controlled. Unfortunately, now it's more like m to the 3/2 rather than m log n. So you're paying a decent price for the quantization. On the other hand, at least n is not showing up terribly. So when you look at relative errors, you could still potentially get small relative errors by doing more overparameterization, but you would like to get this to be smaller. What I should mention is that you could look at a different generalization model and say something like, suppose that my new data point lives within an epsilon ball of an existing data point. Then it's pretty easy to get a nice error bound. You just do a triangle inequality and you're done. So this is not to say that this is the only error bound, but we wanted something where we didn't assume that the neural network was memorizing things and just receiving things that are exactly close by, but something a little bit more sophisticated. Okay. Again, the generalization stuff can be replaced instead of the number of data points by the dimension of the subspace. Okay, so far we've seen an algorithm, we've seen some theoretical error guarantees, we've seen some convincing argument that says you can't expect much better than that theoretically because of things like the discrepancy theory that I alluded to. And now we would like to see if this actually works in practice. So we'll run some numerics, but I need to set it up first because we're not running algorithms over single layer neural networks. We want to run them over multi-layer neural networks. So what are the tweaks that we need? We were previously dealing with this thing. We would like to deal with generalizations of that. So let's just do 2 layers, and then it's easy to see how it goes from there. So all I'm going to do is I'm going to label the output of the unquantized network as y, first layer of the unquantized network as y, and then I label the output of after I quantize the first layer of the network as y tilde. And what I would like is to come up with a Q2 so that Q2 acting on y tilde approximates W2 acting on y. So after I quantize the first layer, I then say I want to quantize the second layer so that I approximate the behavior of the original network as well as possible. And if I do that, I end up with a modification of the algorithm. I mean, you can just run through the same argument. It boils down to basically just rewriting the middle step of the algorithm, and then the update step gets changed accordingly. Just find me the Q that minimizes the error at every step, and then update the error vector. So if you do it this way, you end up with an algorithm. The analysis of this algorithm is a little bit harder because you have dependencies that you're introducing because of the action of the previous layer. So then that's a little more delicate to deal with. We're making progress in that direction, but I'm not exactly ready to write down its theorem here, but though it's pretty promising. Okay, so that's our algorithm. We're going to introduce another practical sort of modification, and that is, and the modification that we're going to introduce is we're going to say, instead of working with something like -101, because I'm working with a real world network where the W's aren't necessarily guaranteed to be in the L infinity ball, they might be in some other scaled object, I'm going to leave the scaling of my alphabet to be a parameter that I choose. And we'll just run through a cross-validation little experiment where we try different scaling parameters and see whether those really affect the performance of the algorithm or how important they are. And I'm going to compare our algorithm to the very simple algorithm that basically says, replace every weight by its closest element in the alphabet. And we'll just see how each one of those two do. So first toy example, MNIST. So just a bunch of handwritten digits. We want to classify them. We're going to train a network which takes in our 784 dimensional digits, run them through a couple of hidden layers, 500 dimensional, then 300 dimensional, and then a 10-dimensional output that basically assigns numbers to each of the digits. Higher number means you classify to it. So 50,000 digits to train this thing. We get a bunch of weights, and now we want to quantize it by replacing these weights by -101. We use 25,000 digits to train our quantization, and then 10,000 to test. And then we're comparing, as I said, to the rounding, to the naive like rounding algorithm. So this is what we are going to see. That's the x-axis is the alphabet scalar that I was telling you about, how you would choose whether it's -101 or -202 or negative whatever. And what you notice is that the performance of the proposed algorithm basically at first is bad if the alphabet scaling is too small, which is not hard to see. If you're quantizing large numbers to very small numbers, you might not be able to do much because you're chasing a vector that is way too large and you'll never be able to catch up to it. But once your scalar is large enough that that problem doesn't really manifest, then you're pretty robust to the choice of scalar. Our algorithm is in blue. Higher is better because that's classification accuracy, whereas the simple rounding algorithm basically really needs it to be tweaked. The alphabet needs to be really fine-tuned to the weights. Okay. And just for fun, to look into the guts of these methods, we thought it would be nice to see how, if I quantize just one layer and leave all the other layers unchanged, how well does the algorithm do? And then when I quantize the next one and leave all the other ones unchanged, how well does the algorithm do? So I want to see if how it's degrading as we move from layer to layer. And what we see is basically the rounding algorithm, because it's completely oblivious. It doesn't look at what's happening at the past layers. It's just replacing each weight by the closest element. At some point collapses. I mean, it doesn't collapse very much, but it loses accuracy in this particular case. Whereas ours is constructed so that it's always error correcting. So at the next layer, it's trying to match the performance of the original unquantized neural network. And it tries to do that in spite of the errors that were introduced in quantizing the first layer. So you see that there's some error correction that is happening from the first layer to the second one, and then a little bit of deterioration, but not a lot. So that was just I thought, an interesting observation that just shows the power of this idea of error correction. Okay, slightly less toyish example, CFAR 10. So here the task is to classify images. We construct a neural network. Here's its architecture. It has convolutional layers, and This is to say that we can modify the algorithm to deal with convolutional, with convolution. And the way you do that is pretty straightforward, because convolution of x with w is also convolution of w with x. So that basically means that if you fix the weight that is unknown and just create an augmented data set with x's that are basically shifted, this augmented data set is what you need to work with for the training. So if you do that, you're in business. And again, some training and testing. And what you see, now I've just added a parameter, which is how big the alphabet is. So do I have 3 elements in the alphabet, 4, 8, or 16? And what is the accuracy of the original network? What is the accuracy of our greedy algorithm? What is the accuracy of MSQ? And you see here that the rounding algorithm is really bad when you have very few bits. Ours is still not ideal, but much better. Both of them improve as you add more elements in your alphabet, but eventually we get much closer to the performance of the unquantized network, which is effectively 32-bit because we're training things on our computer. And there's something like a 5% gap as opposed to a 0.5% gap with the rounding algorithm. Okay, so that's strong evidence that this idea is actually practicable. And if we do the same sort of looking under the hood of the algorithm, we see this, again, error correction property showing itself. On the other hand, the rounding algorithm runs into a layer where the performance goes bad, and then it just can't recover from that. Okay, so these are some observations. They give us positive answers to some questions. Here I've listed Gaussian data, but I should have listed sub-Gaussian and other. But also I only have theory that talks about single layers. In practice, we've seen that with these toy examples and multi-layered neural networks, things work out. So this suggests that the answer to there exists a quantized network that works is generally more likely to be yes. Can we construct it in a reasonable amount of time? That's definitely yes, because our algorithm has these fixed computational complexity. And empirically, we're seeing that it does generalize to new data. But these are proving more about this is interesting and open. So this is a list of some of these questions. We would like to have a proof for multi-layer quantization. We're on our way towards that. It involves dealing with the randomness and the effects of the, you put a randomness assumption on your original data, but then you feed it through a neural network, and then you subject it to these violent nonlinear steps, including ReLU and other things. And then the distribution becomes something different, and you have to keep track of what's going on. You have to come up with properties that get preserved so that your proof doesn't collapse. And we're thinking about this right now. You'd like to weaken as much as possible the randomness assumptions on training data, potentially even remove it if possible, and say something like, here's a deterministic condition on what my training data should satisfy. And then here are some distributions that satisfy these deterministic conditions, but here are also checkable things that you can look at your training data and check whether it satisfies these assumptions. Generalization bounds. Algorithmic modifications are also interesting open questions. In particular, this is sort of the most naive thing you could do, keeping your computational complexity low and being better than just rounding numbers. Now, you could decide that you're willing to put in more computational complexity into your training process in order to get the error to get better. So one thing you could do, for example, is you could quantize the first layer and then say, I'm going to retrain the analog network. I'm going to retrain the network that I'm trying to quantize with the first quantized network layer being fixed. So now you have a new set of W's, and then you go back and you quantize the second layer, retrain everything, quantize the third. And people do this in practice, and it works pretty well, even for scalar quantization, but you can see that it increases the computational complexity quite a bit because there's multiple rounds of retraining, and if the neural network is 100 layers, I mean, good luck. Still, it's worth seeing if something can be said about these things theoretically. You would like to come up with variations that not only replace weights by other weights, but also entirely get rid of layers, for example, or change the architecture of the network into some more favorable architecture. So that's a little bit more, I guess, blue skies at the moment. And more concretely, you could say, well, I want to modify my optimization problem, the one that I end up approximating in my greedy algorithm, so that I promote sparsity in the weights. Why do I want to promote sparsity? Because I want to multiply by zeros as much as possible. And the question is, can you replace this cost function, minimize the L2 norm of the error, by something like minimize the L2 norm of the error plus the L1 norm of the quantized weights or something of that nature, come up with a nice expression for the minimizer and then a proof that this actually works. So here, what I can say is that an algorithm like this works really well. You actually do come up with, it's easy to code up, it's easy to test, and the result is that you see way sparser networks with slightly worse performance. But then the challenge is quantifying the trade-off between the sparsification and the complexity. You can still prove that it works, but it's hard to prove how sparse it's going to be. So that's another kind of interesting open question here. Okay, I think I'm reading 1249 here, so I'll stop.